Hello everyone, this is lecture 4 part 1 of current electricity. Today we will move on with the further discussions of the examples of temperature dependence on resistivity, and then let's go on to different concepts such as power, electrical power, energy, resistivity, different types of resistance either series or parallel, etc. So let's not waste any time. I am Sameer Lavankar. Let's begin our discussion. Okay, so a course outline for you first of all. So in the introduction concept we started with the difference between the movement of charges either at rest or at motion. So we know that after the different charges were being put together, if there is a movement of the charges, then that constitutes an electric current. Then movement can be either in the haphazard manner such as the electrical lightning from the clouds to the earth through the air, or we need to conserve it, we need to move it so that there are very less leakages of current, and hence complete information or energy is being passed from point A to point B. So that complete concept is being understood in the introduction concept. Then the next concept of electric current, we understood what is how the mathematical formulation of electric current takes into picture. So the first was small q by t, that is the number of charges passing from point A to point B or through a area A from point A to point B, that is left side to right side in time t. For infinitesimal method, we understood the concept as electric current is nothing but limit delta t tending to 0 del q upon del t. Then the third concept, we understood that how are the differences in the charges being flowed in a complete substance or material is depending upon how amount is being bounded or it is free to move. The electrons are either bounded or free to move. So if it is very free to move, then these are conductors followed by semiconductors, and then which are very less to move are insulators. Then the fourth concept, we understood the concept of V directly proportional to I. Hence by removing the proportionality constant, we got V is equal to IR. Similarly, R is directly proportional to directly proportional to L upon A. Removing the proportionality concept, we got R is equal to rho L by A. So these were peculiar concepts we understood in this concept of fourth, that is Ohm's law. Then next was the drift of electrons in the origin of resistivity, in which we formulated the formula for small Vd, that is a drift speed, and defined it as drift speed. Similarly, origin of resistivity, in which we found out how is the concept of resistivity came into picture. So basically we denoted everything, we conceptualized the concept of conductivity, that is 1 by rho, and then finally by reciprocal of conductivity we can get the formula for or concept of resistivity. Then the limitations of Ohm law, we found out the different materials such as gallium arsenide, diode, device diode, etc., which do not follow the concept of V is equal to IR, they deviate either in the negative or positive sense or in the same direction also. So these complete concepts were being understood, a small concept only was being understood in the limitations of Ohm's law. Then the seventh concept of resistivity of various materials, we understood the concept of how many types of resistors are possible. So there are carbon type resistors, in which we understood the concept of color coding of different resistors. So these complete concepts were being understood in resistivity. And finally in the last lecture I am explaining you the concept of temperature dependence of resistivity. So we understood that the value of alpha, there is a linear dependence sometimes, and below 0 degree Celsius or 273 kelvins there is a non-linear dependence also. So that complete was being understood using a diagram, using a graph, and then finally the complete concept of linear dependence, that is that the resistivity at some time t is equal to rho naught into 1 plus alpha delta t was being formulated. And finally we understood that for conductors it increases with temperature, and for semiconductors it is negative. For insulators it is the opposite direction of that of conductors. So that was the final concept. Let us move on with the just a quick revision, and then we will move on to explanation part of this only. Okay, so in the final lecture we understood that for insulators and semiconductors n increases with temperature, so that means that the rho decreases with temperature, and similarly for conductors rho increases with temperature. So this was the final concept. Okay, so now let us move on with the small example on this concept only. So an electrical toaster uses nichrome is an element for its heating element. So heating element as in those substances which have a higher capacitance, or not a higher capacity, we can say that which has a higher capacity to change its resistivity, so that the temperature variation with a small increase in, let us say, surrounding temperature, the increase in temperature for that complete element is very high. So if it is very high, it can be used as a heating element. Okay. So an electrical toaster uses nichrome for its heating element. When a negligibly small current passes through it, So if small I is passing through it, its resistance at room temperature is found to be 75.3 ohms. So at T is equal to 27. So if I write it like this, so at T is equal to 27 degrees Celsius, it is in degree Celsius here, it is equal to 75.3 ohms, 75.3 ohms. Okay. Next is when a toaster is connected to a 232 volt supply, so voltage is given to you as 230 volts. I think it is a constant value here. Thus current settles and it attains its steady state after a few seconds to a steady value of 2.68 amperes. So after a steady value of current is given to you as 2.68 amperes. 2.68 amperes. Now what is the steady temperature of the nichrome element? So the steady temperature, that is T naught value, is asked to you if the value of Tc is given to you. So the temperature coefficient of resistance of nichrome averaged over the range temperature range involved is alpha. So alpha is given to you directly. So simple question of directly using the concepts, there is no use of any formula here, so please look over here carefully. So when the current through the element is very small, heating effects can be ignored and the temperature T of the element is the same as the room temperature, quite evident. Because the current, because please make sure why it is happening here, because the current of the element is very small, so heating effects can be ignored. So because of this reason, this is the clause here, that heating effects can be ignored and the temperature T of the element is the same as the room temperature. So when the toaster is connected to the supply, its initial current will be slightly higher than its steady value of 2.68 amperes, but due to the heating effect of the current, the temperature will rise, quite evident, because if the surrounding gives you a temperature higher, then the temperature will rise. This will cause an increase in resistance and a slight decrease in current. So therefore the value of I dash was higher and the previous portion, and it decreased. Why it decreased? Because there was an increase in the temperature. In a few seconds a steady state will be reached. So I explained you that this is nothing but the current settling is nothing but a steady state being achieved here. When temperature will rise no further and both the resistance of the element and the current drawn will achieve steady values. Hence the answer of this question, it is just this, that the steady temperature is the same as the room temperature, which is equal to 27 degrees Celsius. But just to explain, if it is being asked that the current value was greater or higher before the heating has been done. So just to explain this line is given to you, that when the toaster is connected to the supply, the initial current will be slightly higher than the steady value of 2.68 amperes. Therefore I dash will be greater than I, where I is the steady current. Okay, so just so this example was here just to explain to you that sometimes there is no use of formula also, you just need to be thorough with the complete theory so that you can understand that the steady current temperature is being asked is nothing but the value of same 27 degrees Celsius only. You won't go into multiplying the formula as rho T into 1 plus alpha delta T here and so on. Okay, let us move on to the next example now. So that resistance. So the resistance of the platinum wire of a platinum resistance thermometer at the ice point. So ice point, please remember what is ice point. Ice point is the temperature at which ice is formed, is 5 ohms, and at steam point, what is steam point? Steam point is the point at which the steam is obtained. Steam is obtained at 100 degrees Celsius, is 5.39 ohms. When a thermometer is inserted in a hot bath, the resistance of the platinum wire is 5.795 ohms. So you just need to calculate the temperature of the bath. So the first two lines are being used to find out the value of alpha, and finally using this alpha obtained, you can directly find out the value of the temperature of the bath, given that you know this temperature, you know this resistance also, and you know the initial resistance of maybe let us say hot bath or steam point, or let us say ice point. So it is a simple mathematical calculation done twice. So you just need to use this formula only, that is what we can say, rho T is equal to rho naught into 1 plus alpha delta T. You just need to use this formula twice and then you will get your results. Okay, so how are they using the formula here? So it is just that they are using it as a resistance value. So just to explain to you how it is happening here, alpha delta T. So here see, as you can see, R naught. So R naught is given to you. R naught is nothing but the resistance of the thermometer at ice point. So it is R naught, which is given to you as 5 ohms. Then similarly R100 is given to you, that is R100 is nothing but at the steam point, which is equal to 5.39 ohms. 5.39 ohms. The next point is that value of RT. So RT is nothing but we need to find out the temperature. This temperature is unknown to us. This temperature is unknown to us, which is at 5.795 ohms. Okay. So now so this formula can be changed into this form, that is rho T minus rho naught upon rho naught is equal to alpha delta T. Now if I try to make this for the two simple examples here, so it will be nothing but just to explain to you, if I take every value from the value of initial point here, then it will be equal to, let me explain to you here. So rho T minus rho naught. So it will be nothing but if I take first of all those two examples of 100 degree Celsius and 0 degree Celsius. So it will be nothing but R 100 minus R naught upon R naught is equal to, alpha will be same for both and T will be delta T. Delta T will be nothing but 100 minus 0 here. Similarly for the, let us see I write this as equation 3, and similarly if I find out for RT and choose it for R naught value here upon again R naught is equal to alpha delta T. So using just equation 4 and 3, if I divide equation 4 by equation 3, that will be nothing but delta T, which I need to obtain, upon 100, because different temperature difference is nothing but 100 for 100 and 0 here, is equal to RT minus R naught upon R100 minus R naught. Therefore this temperature delta T, because the initial point is your 0 degree Celsius only, therefore delta T will be the final value obtained in degree Celsius, which is equal to nothing but RT minus R naught upon R100 minus R naught into 100. Hence this is the equation which is being obtained here. This is a similar equation here. You can either remember this equation or you can just use this complete concept to find out the value of resistance at temperature T. Okay, so now just substituting the value of RT, R naught, R100, you will get the value of T, that is temperature, is equal to 345.65 degrees Celsius. So the temperature of that bath was nothing but 345.65 degrees Celsius. So simple mathematical formulation only, you just need to remember this formula, that is rho T is equal to rho naught into 1 plus alpha delta T. Because rho is directly proportional to R, and if the so why we are using the value of resistance, because we know that resistance is nothing but rho into L by A. So we can write rho is equal to nothing but R into A by L. Because the value of A and L was constant every time, therefore we can just cancel A by L on both sides, and we will get the formula to be same here also. Okay. So this is the end of the example statement. Let us move on to new concept now, that is electrical energy and power. So what is electrical energy and power? Let us try to understand everything here. So this thing is being added subsequently. This is the complete formula sheet here. I think in the last point we understood the concept, last point we understood the concept of mobility also. So I have added that also here, that is mobility is nothing but E tau by m. What is E? E is the charge of the electron. What is tau? Tau is the relaxation time. What is m? M is the mass of the electron. Okay. So please look very carefully, new concept now. So consider a conductor with end points capital A and capital B, in which the current I is flowing from A to B. So let me just make a conductor here. Let us this is the conductor being formed here, let us say this is the point A, let us say this is the point B, in which a current I is flowing from A to B. So let us say the current direction is this. The electric potential at A and B are denoted by V of A and V of B. So let us say the electric potential is denoted by V of A here and V of B here. Okay, since current is flowing from A to B, quite evident so it's the assumption only here, VA is greater than VB, quite evident. Why it is evident? Because always we know that the anything passes from a higher potential to lower potential. So if the passage of current is from A to B, then that means it is V of A is greater than V of B. So this thing is okay. So let me write it again here, that is V of A is greater than V of B. Okay. And the potential difference across AB is nothing but V, quite evident, because if these are the potentials, then capital V is nothing but V of A minus V of B, and from the above equation, above inequality, we can say that this is nothing but positive. Okay. So in a time interval delta t, an amount of charge delta q is equal to I delta t travels from A to B, quite evident. Using this formula here given, that we can find that the delta q is nothing but I delta t. because I is constant, so I delta t. So this amount of charge has been flown in time delta t from A to B, quite evident from A to B. So the potential energy of the charge at A by definition was QVA, and similarly at B it is QVP. So potential energy is nothing but a charge multiplied with the potential. So therefore we can find that the potential energy, let me write the potential energy directly here. So PE at A is equal to capital Q into V of A, and PE at B, it is just a definition, please do not go into different details here. The definition of potential is nothing but charge multiplied by potential energy, charge multiplied by potential. So Q into V of B. Okay, so this thing is been explained. This is just we are making a model so that we can understand the concept of electrical energy and power. Okay, thus the change in the potential energy delta U potential will be nothing but it is a simple method, it is just a simple difference of these two methods here. So we can write it as delta Q into V of B minus V of A, because always when we try to find out the change in the potential energy is nothing but final minus initial. So what was final value? Final value was B for you. What was initial value? Initial value was A for you. Therefore we will write VB minus VA and not VA minus VB. Okay, so it is nothing but delta Q into capital V. Capital V is nothing but the potential difference, but here quite evident as VA is greater than VB, therefore we will get this value is negative. So just writing minus V here. Also we can write this equation as changing delta Q from this equation here, we will write as minus I delta T into V. Quite evident as the value is negative and these all things are positive, hence the complete value will be negative here. So that is the same thing which we obtained here, that the delta U potential will be nothing but negative. So if charges moved, this thing is also been explained. So now if charges moved without collision through the conductor, the kinetic energy would also change, so that total energy is unchanged. Quite evident that if the charge is quite, we know that for the electric current to take place there has to be a collision, and if the collision is happening, if charges are moving without collision through the conductor, the kinetic energy would also change, so that the total energy is unchanged. So if the charges are moving without collision, assuming there is no energy, though there is no change in the energy of an electric charge is happening, that means the energy is conserved, and if the energy is conserved then the kinetic energy would also change, because there has to be no change in the total energy. If there is a change in the potential energy, then there has to be change in the kinetic energy, so that the complete energy is conserved. Okay, so the charges moved without collisions through the conductor, the kinetic energy would also change. Why it will change? Because we need to conserve total energy, so that the total energy is unchanged. Okay. Next is conservation of total energy would also imply that delta K is equal to minus U potential. Quite evident, as we know that how can I explain to you? Let us say I write delta total energy is equal to 0, because energy is always conserved. So delta total energy is nothing but delta kinetic energy plus delta potential energy. Potential energy, I am writing potential energy is 0, U pot is equal to 0. So now quite evident from this example here, it is nothing but delta change in kinetic energy is nothing but minus change in potential energy, because we need to conserve total energy. Now from this concept, as we know that U potential is nothing but minus I delta Vt, therefore we can find that delta kinetic energy, that is change in kinetic energy, is nothing but I V delta T, and hence this value is positive. So this is the final. So just to conclude this complete concept here, we just took a model from VA to VB, we found out the value of potential difference for it, we found out the value of potential energy for it, we found out the value of delta Q, that is charge passing from point A to point B. Now what we did was we found out the value of change in the potential energy. For the change in the potential energy, that will be nothing but the charge flowing, that is potential energy final minus potential energy initial, that is equal to QVB minus QVA. Using the value of Vb minus Va, we found out that the value was negative, and we found out that it is equal to minus IV delta T. Now for the total energy to get conserved, we know that the change in kinetic energy plus the change in the potential energy should be equal to 0. Therefore the change in kinetic energy should be equal to negative of the change in potential energy. Now we found out the change in the potential energy to be minus IV delta T. Therefore the change in the kinetic energy will be nothing but plus IV delta T. So that is the end of this. I may continue this discussion in the next part. So let me stop it here only. Then finally in the next concept we understood the concept of change in the energy, what are the formulas of P, that is I square R, V square by R and so on. So let me stop it here only. I will start from this concept in the next lecture. So thank you.